Have you ever thrown a ball into the air and watched it arc beautifully before landing? That elegant curve is physics in action, and we call it projectile motion. A projectile is any object that is thrown or launched into the air and then moves only under the influence of gravity. There's no engine or force acting on it after launch, just gravity pulling it downward. What makes projectile motion unique is that it happens in two dimensions, horizontally and vertically, at the same time. While gravity pulls the object down, its initial push gives it forward motion. Together, these two motions form a parabolic path, something you can easily observe in sports, fountains, or even fireworks. Now let's dig into the components of motion that define a projectile's journey. In the horizontal direction, there's no force acting after launch, so the object moves with constant velocity. No acceleration here. Vertically, however, gravity takes control, pulling the object downward with a constant acceleration of 10 meters per second squared. This creates a uniformly accelerated vertical motion. To analyze this, we break the initial velocity into two parts, horizontal and vertical. The horizontal component is ux equals u multiplied by cosine theta, and the vertical component is uy equals u multiplied by sine theta. Let's now derive the equations that help us calculate position and velocity at any moment during projectile motion. Horizontally, there's no acceleration, so the displacement is x equals ux multiplied by t, where t is the time. Vertically, it's uniformly accelerated motion. The vertical displacement is given by y equals uy multiplied by t minus half multiplied by g multiplied by t squared. These two equations allow us to predict where the object will be at any time. But we can go a step further. By eliminating time from these expressions, we get the trajectory equation y equals x multiplied by tangent theta minus open bracket g multiplied by x squared divided by 2 multiplied by u squared multiplied by cosine squared theta close bracket. Projectile motion has three key quantities that help us understand and predict the motion. First is time of flight, how long the projectile stays in the air. It is given by t equals to multiplied by u multiplied by sine theta divided by g. Second is maximum height, which is the peak point in the motion. It's given by h equals u squared multiplied by sine squared theta divided by 2g. Third is range, which is the total horizontal distance covered before landing. It is r equals u squared multiplied by sine of 2 theta divided by g. Each of these formulas comes directly from our vertical and horizontal motion equations. And together, they define the full story of projectile motion. In the figure shown, we can clearly identify the range, the time of flight, and the maximum height. Projectile motion has some fascinating characteristics that make it predictable and symmetric. The path is perfectly symmetric, which means the time taken to go up is equal to the time taken to come down. At the highest point, vertical velocity becomes zero, but the horizontal velocity stays constant throughout. One of the most interesting results is that the range is maximum when the angle of projection is 45 degrees. Even more surprising, two angles that add up to 90 degrees, like 30 and 60 degrees, will give you the same range for the same speed. This is why sports like basketball or cricket rely so much on the angle of launch for the perfect shot. Let's now solve a problem together to apply all that we've learned. A body is projected with an initial speed of 20 meters per second at an angle of 45 degrees. We are to calculate the time of flight, maximum height, and horizontal range. Given u equals 20 meters per second, theta equals 45 degrees, and g equals 10 meters per second squared. Time of flight t equals to multiplied by 20 multiplied by sine of 45 divided by 10, That gives us approximately 2.83 seconds. Maximum height h equals 20 squared multiplied by sine squared 45 divided by 2 into 10, which comes out to approximately 10 meters. Horizontal range r equals 20 squared multiplied by sine of 2 theta divided by 10, and that gives us approximately 40 meters. So, the object stays in air for about 2.8 seconds, reaches a height of 10 meters, and lands 40 meters away. The diagram here shows this complete motion visually. Let's quickly recap what we've explored in projectile motion. It is a two-dimensional motion where horizontal motion is uniform and vertical motion is under constant acceleration due to gravity. The trajectory formed is a parabola, and important parameters include time of flight, maximum height, and range. We saw how complementary angles give the same range and how a 45-degree launch gives the maximum horizontal distance. From sports and engineering to fountains and firework displays, projectile motion is everywhere in our world. I hope you now understand how this beautiful motion results from the interplay of two independent forces. See you in the next session with another fascinating concept of physics.